we're in section 8 point, what are we doing today? 8.3? 8.3. So geometric sequences and series. Let me do this. All right. So last time we talked about arithmetic series and sequences. And arithmetic sequences and series are when we found each successive term by adding a constant to the previous term. Similar, we're going to go through the process working with geometric series in a very similar way. Geometric series, the way we define a geometric series is we find each successive term by multiplying by a constant. And the way we write that in symbols is we're going to say that a sub n equals a sub n minus 1 times r. Or we could also say that a sub n over a sub n minus 1 equals r. And we call r the common ratio. So where with arithmetic series we have a common difference, with geometric series we have common ratio. Arithmetic series have to do with addition, geometric series have to do with multiplication. So let's look at a couple of easy examples here. So let's say we had geometric series 3, 6, 12, 24, etc. Definitely not an arithmetic sequence, because 3 plus 3 is 6, but 6 plus 3 is 9, not 12. So when we're trying to tell, we don't know for sure what kind of sequence we have. Arithmetic, if it looks like it could be arithmetic, that would be our first try. Second try, geometric. Because arithmetic series sequences and series and geometric sequences and series have nice properties that we like to use. So what would be our common ratio here? R equals 2. So that one's easy. How about 1, 1/2, 1/4, 1/8, etc. What would our common ratio be there? 1/2. Because we multiply 1 times 1/2 equals 1/2, 1/2 times 1/2 equals 1/4, etc., etc. And now that we're talking about geometric sequences and series, now I have a whole new series, no pun intended, math jokes that I can tell that have to do with series that I couldn't tell at the beginning of the year because we hadn't studied series yet. All right, so a common ratio, we're just multiplying each term by a constant number. So what we want to do is, like what we did with arithmetic series, arithmetic sequences, is we want to find the formula for the nth term. How do we find the nth term? And we want to see if we can find a formula for the sum. And that lets us work with these sequences and series in different ways. So let's come up with our formula for the nth term. Or nth term formula. So we're going to start with a sub 1, just like we did before. A sub 2, for a geometric series, is going to be a sub 1 times r. A sub 3, we multiply the previous term by r, so a sub 1 times r times r. And what does that give us? A sub 1 times r, r squared, right? R times r is r squared. A sub 4 is going to be a sub 1 times r squared times r, which is going to be a sub 1 r to the third. And if we keep going, a sub n is going to be a sub 1 r to the what power? N minus 1. So very similar formula, but now we have an exponent rather than multiplication. So this is our nth term formula. A sub n equals a sub 1 times r to the n minus 1. So this is going to be one of the formulas that we use with geometric sequences and geometric series. Now just as a side note, in this particular book, we're starting our geometric sequence with a sub 1. Some books, you'll see geometric sequence, they start with a sub 0. And then they go from a sub 0. And then if we start from a sub 0, then our formula is a sub n equals a sub 0 r to the n. So we're just going back by one number on our index. So just, it's not, if you see it written that way, it's not different. It just depends on where we start counting. Here we're starting with 1. Sometimes some books like to start with 0. All right, questions on our formula. All right, so let's use this formula to do a couple of examples. Let's say we want the nth term. This one's easy. So we have a geometric sequence with a sub 1 equals 5 and r equals 2. So this one's really easy. It's just asking us to plug these numbers in. So a sub n is 5 times 2 to the n minus 1. If we wanted to simplify this at all, is there another way we could write this? How do we go? Can we go backwards? So n minus 1. So when we add two numbers as an exponent, what are we doing with the base to the power? Do we remember? Multiplying. So I could write this as 5 times 2 to the n times 2 to the minus 1. And we could also write this as, so 2 to the minus 1 is 1 over 2. So this could be 5 halves 2 to the n, and that would be the same thing. This is fine, but you might also see it written like this. All right, questions there? This answer would be, if I asked you this, or if you got this in the homework, this 5 times 2 to the n minus 1, that's fine. Just wanted to remember a little bit about how we work with exponents. All right, let's do another example. For this one, we want to find the 20th term of our geometric sequence And for this particular geometric sequence, and not width, I'm just going to give us the numbers. 1, 3, 9, 27, dot, dot, dot. So we want the 20th term of this geometric sequence. So for this one, what is a sub 1? A sub 1 equals 1. What is r? 3. So we want the 20th term, so a sub 20 is going to be 1 times 3 to the 19th power. And if I calculate that out, 3 to the 19th power is 162, 261, 467. So the 20th term of this geometric sequence is over 1 billion. Geometric sequences grow extremely fast if our common ratio is a whole number, is larger than 1. So our sequences grow very, very quickly. And this r equals 3, that's not particularly a big number. So imagine if our common ratio were something like 10 or 15 or 32, something like that. Our terms would grow really, really large, really, really, really fast. So that's something to keep in mind, and we'll use this idea a little later when we talk about the sum of a geometric series. All right, questions there? All right, so let's look at an example like we did with our arithmetic series where we have 2 terms and we want to find some information about our series from 2 terms, or about our sequence with 2 terms. So we want the 15th term find the 15th term of the geometric sequence with, let's see, the 3rd term, a sub 3 is 5/4, and a sub 6 equals 5/32. So we're going to go through a similar process to the one that we did with arithmetic sequences. This tells us 2 pieces of information. So we're going to use these 2 terms to write 2 equations. We have 2 pieces of information, so we're going to write 2 equations. So I know that a sub 3 equals a sub 1 times r squared. That's our nth term. And that equals 5/4. And a sub 6 is a sub 1, r to the 5th. And that equals 5/32. I have 2 equations and 2 unknowns. I have a1 and r. So I need to use these 2 equations and solve for a1 and solve for r. Anybody see how we might be able to go about doing this? Not quite as easy as the last one because we don't have a nice 3x1 plus 5y, 3x times 5 plus 5y equals 7, those kinds of equations. Our equations are a little more complicated. You have an idea? You're thinking try to figure out our common ratio by looking at trying to find a pattern here. Okay, so that's one possibility, and especially since these two are fairly close together, the third term and the sixth term are fairly close together, we can see if we could guess at the common ratio based on the information we have here. If these were really far apart, that would be a little more difficult. So that's definitely a technique that we could use. I want to try to use a technique like we used the last time. So what I'm going to do is I'm going to solve this first equation for A1. So I get, when I get A1, when I solve for A1 here, I get A1 equals 5/4 times 1 over r squared. So I'm just dividing both sides by r squared. And now I'm going to substitute this in to the second equation. So I'm going to substitute this A1 into the second equation. So I get 5/4 times 1 over r squared times r to the 5th equals 5/32. Well, now I just have one variable here, so I can simplify this. First off, what is 1 over r squared times r to the 5th? Justin says r to the 3rd. So let me rewrite this. This is 5/4 r to the 5th over r squared, and that equals 5/32. This should be r squared r to the 5th here. R to the 5th over r squared is r to the 3rd. So I get 5/4 r to the 3rd equals, and this should be 5/32. 5/32. I multiply both sides by 4 and divide by 5. So r to the 3rd equals 5/32 times 4/5. 5's cancel, and the 4 goes into the 32 8 times. So r to the 3rd equals 1/8. To isolate r, I take the cubed root, and r equals 1/2. And that's what you were saying just a second ago. You saw that r equals 1/2. Now I have r equals 1/2. I can substitute that into either of the equations to solve for A1. Now we're going to solve for A1. So I'm going to say A1 times 1/2 squared equals 5/4. So A1, what's 1/2 squared? 1/4. A1 times 1/4 equals 5/4. So A1 equals, multiply both sides by 4, A1 equals 5. So I solve for A1, or I solve for A1 here, substituted into the other equation to get R. Then I substitute that into this first equation to find A1. And now we can solve our problem. The problem asks us for the 15th term of this geometric sequence. So A sub 15 is going to be 5 times 1/2 to the 14th power. And when I calculate that out, I get 5 over 16384. So for my first step, I solve for R. My second step, I solve for A1. And then finally, I was able to answer the question. So doing a very similar process to what we did with the arithmetic sequence, where we had the same kind of problem. Questions there? Okay, let's come up with our sum formula. So we found our nth term formula, we used the nth term formula to solve a few problems. Let's come up with our sum formula. So first we're going to sum a finite geometric series. And we'll use this formula that we come up with for this one to come up with the sum of an infinite geometric series. And we've found the sum of a couple of infinite geometric series already. We talked about the repeating decimal. We did an example of that the other day in class. You did a couple in the homework where you found the repeating decimal, this series that summed to a repeating decimal. We're going to talk about that a little more. All right. So what we're going to do is, again, like we did for our arithmetic sequence, our arithmetic series, we're going to write out this sum. So S sub n is going to be a sub 1 plus a sub 1 times r plus a sub 1 times r squared plus dot dot dot. And our last term is a sub 1, or let's just say, yeah, that'll work, a sub 1 r to the n minus 1. So that's our nth term. So, and we're adding those together. That's what we mean when we say we have a series. Now our trick for this one, we're not going to write this one backwards like we did for our arithmetic sequence, but we're going to multiply this by r. So r s sub n. I get, when I multiply this, I get a sub 1 times r plus a sub 1 when I multiply this by r, a sub 1 r squared, plus when I multiply this by r, a sub 1 r to the third, plus dot dot dot, plus, and when I multiply this by r, I add 1 to the exponent, I get a sub 1 r to the n. And here's the really cool thing with this. Now I'm going to subtract this equation from this equation. So I get s sub n minus r s sub n equals, when I subtract these two, here's a sub 1 r minus a sub 1 r. A sub 1 r squared minus a sub 1 r squared. I'll have an a sub 1 r cubed minus a sub 1 r cubed, etc., etc., etc. And out here, this term right before this is going to be a sub 1 r to the n minus 1, and those will cancel. And all I'm left with is the first term, a sub 1, minus a sub 1 r to the n. All these terms in the middle cancel out. They all subtract away. I'm going to factor the common term here of s sub n. S sub n times 1 minus r equals, factor out the common term of a sub 1. And I get my formula, s sub n, divide both sides by 1 minus r, a sub 1, 1 minus r to the n, divided by 1 minus r. And that is our sum of a finite geometric sequence. So I need to know my first term, I need to know my common ratio, and I need to know how many terms I'm adding up. And this will let me find the sum of a finite geometric series. The couple of ways that you might be asked this question, the sum of a finite geometric series, the sum of n terms. Or the nth partial sum. Both of these things mean the same thing. It means add up in terms. So questions on our formula. I really like how this one where all this stuff cancels out in the middle. That's kind of nice. All right, let's look at an example of finding a partial sum, and then we will talk about the sum of an infinite geometric series. We'll use this formula to come up with our idea for the sum of the infinite geometric series. All right, so let's say we want to evaluate the sum, sigma notation, that's what this is called, sigma notation, just as a reminder, n equals 1 to 20 of 2 times 0.1 to the n. So this would be the sum of 20 terms, the 20th partial sum. Those would be a couple of different ways that this could be asked. So first off, is this a geometric series? We're saying kind of, sort of, thinking yes. What would be our common ratio? R is going to be 0.1. And if you're not sure, you could write out some terms. So this is 2 times 0.1 to the 1 plus 2 times 0.1 squared plus 2 times 0.1 to the third plus dot dot dot. So if you're not sure, you could write it out this way. So we see that we're multiplying each term by 0.1. A sub 1, what's the first term going to be? What's 2 times 0.1? 0.2. So my sum of 20 terms, S sub 20, that 20th partial sum, is going to be A1, which is 0.2, times 1 minus 0.1 to the 20th power over 1 minus 0.1. And if I calculate that out, this comes out to be 2/9. Questions? All right. Now let's write down, or let's talk about the sum. The last thing we need to talk about the sum of an infinite geometric series. So let's look at our sum formula again. We said that S sub n equals A1, 1 minus r to the n over 1 minus r. Now I want to look at the exponential function r to the n. If r is a fraction or a decimal, and the way that we write that in symbols is we say the absolute value of r is less than 1. If r is a fraction or a decimal, what is the horizontal asymptote of an exponential function like this with the base a fraction or a decimal? 0, right? An exponential function with a base that's a fraction or a decimal looks like this. And it has a horizontal asymptote of 0. So as r gets very, very, very large, way out here, r to the n gets closer and closer and closer to 0. If our common ratio is a fraction or a decimal, the absolute value of r is less than 1, this number r to the n, as we sum more and more and more terms, as n gets very, 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 very large, this number on the top gets very, very, very close to 0. And if, as we sum more and more and more terms, this r to the n gets smaller and smaller and smaller, and after a while, it's so close to 0 that we just say it is 0. It's so close to 0 that it's essentially 0. So the sum of an infinite geometric series. So the sum, n equals 1 to infinity, of a sub 1 r to the n minus 1 equals a sub 1. I'm subtracting 0 from 1 here, so all I'm left with is a sub 1 over 1 minus r. If the absolute value of r is less than 1. So if our common ratio is a fraction or decimal, less than 1, we can sum an infinite number of terms of our geometric series and we get a number. Because each of these keeps getting smaller and smaller and smaller and smaller and smaller, and pretty soon they just don't matter anymore. So this is our second important sum formula for an infinite geometric series. If r is larger than 1, what is this infinite sum going to be? Infinite, right? Because the example we did before where the 20th term of our sequence with r equals 3 was over 1 billion, those numbers get large very fast and we're adding them, a bunch of them together. So the sum of an infinite geometric series where r is bigger than 1 is going to be infinite. Where r, absolute value of r is less than 1, then we get a number. So let's look at a quick example of this, and then that's all we needed to talk about today. Sum of n equals 1 to infinity, 2 times 0.4 to the n minus 1. First off, is this geometric? Yes, r equals, what's our common ratio? 0.4. A sub 1, 2, because my first term I plug in n equals 1, and I get 0.4 to the 0, which is 1, so our first term is 2. So our sum equals 2 over 1 minus 0.4, and that equals 10/3. And we can leave it written as a fraction. So what I did to get this 10/3, this is 2 over 1 minus 4/10. So this turns into 6/10 minus 4/10, and that's where I get that 10/3. All right, questions there? All right, so keep this in mind tomorrow when I tell my math joke, because it will involve this idea. It'll be kind of fun. All right, homework. It's a fair number of problems, but we have a fair amount of time. can't read the others. Jackson. What do I have? 82 and 105. There we go.